Welcome to EDU World Space.
So in this question, we are given a stainless steel cylinder, right? Um, Stainless steel cylinder, and its inner its inner diameter is equal to 4 inches, right? And the wall thickness is equal to zero point 0.1 inch, right? Um, Now, if it is subjected to an internal pressure of 80 psi and an axial load of 500 pound, right? And a torque of 70 pound per feet, right? So we need to that determine that whether yielding occurs or not, right? Yielding occurs or not according to maximum shear stress theory, right? So let's start with the solution. The solution is a little bit lengthy, but it's very simple, right? So the solution, we are going to start the solution by finding the in stresses, right? The stresses that are created by the internal pressure P, right? And to do so, we are going to use chapter 8 theory. Now, the chapter 8 theory, it only applies for thin walled vessels, right? And that have a ratio of the radius of the wall thickness of at least 10 inches, right? So in our case, it would be R divided by T, 2 divided by zero point 0.1, and that is equal to 20. Now 20 is greater than 10, right? So it means that we can use this chapter 8 theory for thin wall vessels, right? So now what we're going to do is that we are going to find out these stresses, right? These stresses are sigma 1 and sigma 2. Now the thing to note over here is that they are not principal stresses, but in this case we are going to use equation number 8.1 and 8.2, right? So we will be using the same annotation, but keep in mind that they are not principal stresses, right? These are the stresses that are created by the internal pressure P, right? So let's find out these stresses, sorry. So sigma sub 1 is equal to P times R divided by T. Just plug in the values and we'll get that 80 times 2 divided by zero point 0.1 is equal to 1600 KSI, right? And sigma sub 2 is equal to P times R divided by 2T. So that is equal to 80 times 2 divided by 2 times zero point 0.1. That is equal to 800 PSI, right? And sorry, this is also PSI. Okay. So now it is okay. So now what we are going to do is that we are going to find out the normal stresses, right? The normal stresses that are created by the force, um, axial force F, right? Now the outer radius, it would be R naught plus T, so that is 2 plus zero point 0.1, right? That is equal to 2.1 inch. Now we are going to find out this normal stress. So we have sigma sub fx equal to F divided by A. Now plug in the values and we get that F divided by pi times R naught squared times Ri square, right? Plug in the values and we get that it is equal to 388.4 psi, right? So now let's move forward since we have our stresses. Right? So we found in problem 10.59, right, that the distortion energy theory, it can be written in terms of sigma x, sigma y, and tau sy, right? So it means that we can use this equation that is equal to sigma sub x square negative the product of sigma sub x sigma sub y plus sigma sub y square plus 3 times tau xy square, right? So now we have a tau is that creates a shear stress, right? Now recall your previous knowledge of chapter number 5, right, that deals with torsion, right? And we are going to use equation 5.6 from this chapter. So that would give us torque is equal to T times R naught divided by J, right? So R naught divided by pi by 2 R naught raised to power 4 negative R sub I raised to power 4, right? So just plug in the values and we'll get that torque is equal to 325.85 KSI, right? Now, next we have to figure out the direction of the um, stresses, right? So look at the direction of the stresses sigma sub 1 and sigma sub 2, right? Again, from chapter number 8, we will be using chapter number 8 theory. Now, we see that sigma sub 1 is in the y direction, right? And sigma sub 2 is in the x direction. Fine. So now let's recap that sigma sub x is equal to sigma sub 2 plus the normal stress, right? That is equal to 800 plus 388.4, that is equal to 1188.1 psi. Excuse me, psi, right? And sigma sub y is equal to sigma sub 1, that is equal to 1600 psi, right? And tau is equal to 325.85 psi. So now that we have all of these values and the direction, so we are going to find the principal stresses to see that what form of equation 10.27 we would be using. So the principal stresses would be found out by using equation 5.9, right? So sorry, it's 9.5. 9.5. So sigma sub 1 is equal to sigma sub x plus sigma sub y divided by 2 plus under root parenthesis sigma sub x negative sigma sub y square divided by 2 plus tau sub xy whole square, right? We have all of these values, just plug them in and we'll get that sigma sub 1 is equal to 1.778 ksi, right? Next we are going to find out sigma sub 2, right, the principal stress, right? Um, so this would be sigma sub x plus sigma sub y divided by 2 negative under root sigma sub x negative sigma sub y parenthesis close divided by 2 plus tor sub x y square, right? Again, just plug in the values and we'll get that sigma sub 2 is equal to 1.008 ksi. Now, since the two principal stresses have the same sign, then equation 10.27 tells us that the highest principal stress is smaller than the yielding stress and the material will not fail, right? So, look at page number 882, right? And we see that the yield stress for our material is 30 ksi, right? And because sigma sub 1 is equal to 1.778 ksi and it is less than 30 ksi, so it means that the material does not fail, right? Material does not fail, right? So this concludes our answer.